Morning, Bill.
Good morning.
Are you this morning? What's the weather like up there?
Oh, well, perhaps we're enjoying some of the weather that you had a few weeks ago.
Oh, really?
I remember you said it was particularly rainy and that you had problems with your roof. Well, today it's raining, although it's still today. It's also relatively cold, just slightly above the freezing point, and so it's raining, and there is some ice accumulation on the trees, which is unusual for this time of year. Like it'll happen sometimes during the winter, but
You're in Ottawa. You're in Ottawa?
just south of Ottawa, yeah.
Okay.
It's part of the same weather system that sort of came through the mid US there over the last day or so.
That's wreaking havoc everywhere. 30 people killed here, 30 people killed there, homes destroyed, and so on.
Yeah, very severe storms. Here we seldom get that kind of severe storm, but we do get the rain.
Yeah, Professor Cruz is on.
Hi, how are you?
Good morning.
Good morning.
Good morning.
So I'm pretty excited about some ideas on that last page. I sent you page 5. I've actually talked about the other material, but it's important, so I kept it. But page 5 is really the interesting thing, I think, that's new.
Yes, I did. Excuse me. I did read through, first reading of your draft, and it got to the interesting part and then stopped.
Oh, okay. Well, that's page 5.
Yeah,
Because,
I thought,
actually,
oh well, this is where I like to see the next section. Like, where do we?
Because it really, thanks to the fact that I was thinking, what do I have? I actually discovered these new things just 15 minutes ago, even more interesting. Anyway, I think it's extremely interesting, and I think it's simple, and it can be developed, and it might be significant in quantum mechanics. I think you said you're very interested in quantum mechanics. It might reveal internal structure of quantum particles, photons, or whatever. Anyway. So I'd like to, I hope that I can get you guys interested. I like to, if we could write a joint paper, I'd be very happy about it. Because you're really the physicist. I'm half physicist, half mathematician. And of course, the connections to graph theory, I think, is very interesting too, but we could concentrate more on these new ideas that I'm trying to tell about in page 5 there.
For me, the application to physics still seems fairly speculative, but the sort of the formal aspect in Clifford algebra does seem quite interesting.
Well, basically, what I'm saying is that really the most basic extension of the real numbers are to include these nilpotents, which are correlated in the sense that their inner product is equal to 1/2, which makes it, A1 times A2 plus A2 times A1 is equal to 1, which is kind of like duality as well. And well, nilpotents, of course, light rays travel on the light cone, so that these are light cones, and now it looks like, well, I wanted to let Professor Cruz, he was going to talk about, try to fill in what I missed, I guess, and we can, if he leaves me some time, we can talk about these ideas as well.
Yes, I only organize some ideas that Professor Page and I were speaking the last meeting. Then I'm going to present this. I have a slide, and I have no problems. I proved the video conference after of meeting Professor Pesh, and not a problem with sharing my screen. I hope this work
yeah.
okay today.
Yeah, you had some difficulty with that last time, but
Yes. Mhm.
okay. Well, I can tell you what I see at the moment.
Then
Again, it
you
says
can
screen
see
broadcast.
my presentation.
I cannot. I
Well, it's
see.
something that's not normal. I can't read it.
It says everything on your screen, including notifications, will be recorded. Enable do not disturb to prevent unexpected
Yeah,
notifications.
that's what I see too.
But not yet the presentation.
No presentation yet. Only a screen that looks like it comes from a Mac or iPad, and it is suggesting, I think it's waiting for confirmation. It looks like it's waiting for the confirmation that you want to share the screen.
I don't know what's wrong because
The specific, well, I don't know, maybe I could send this by email or something. New options.
okay.
Yeah, it says screen broadcast at the
Because
top.
I test after of our meeting, and then I get this working okay without any kind of problem. But I don't know what's wrong with this.
Maybe try it again, close it and open it again. Maybe it'll be normal.
Yes. Maybe it's close. Okay. Okay, I'm going to share.
No, same thing.
And now, did you get it?
Oh, we see exactly the same window as last time.
Now it says screen broadcast. Can you click on screen broad? You don't see that, I guess, Jesus. It says screen broadcast with a red dot. Maybe you need to click on that or something. It does say Zoom. I don't know what it means, of course.
Okay, and then
I might have the same trouble if I try opening mine. I don't know. Maybe something's different on Zoom now.
As I can see now that not yet, then I'm going to stop here sharing and I'm going to share here.
That looks better.
Okay, that's it.
Okay. Wait a moment. Only I need this for monitor my own screen. Okay, then I'm going to the first. Maybe we can start with this idea of some standard graphics that are published in literature. Then maybe I can run the slide. Okay, I think it is better.
Yes, that's perfect.
Then we go to the next. Here we have a kind of graphs that are a complete graph. We can see here a complete graph with nodes 3, 4, and 5 respectively. You can see how this is increasing the complexity of the graph. And then, sorry, I need to put my dog out of here because it's annoying me. Sorry. Oh, sorry. Here again. And then, okay, we go to the next. Here, I am showing this complete graph, putting apart the arrows with the weight +1 and -1. Then it is interesting to see how this weighted graph are showing to us that there are inside a complete graph different kinds of information that we need to put separate, because not all the arrows are the same, and then they show to us different properties in the graph. Okay, then I go to the next. One way of looking at it in a better form is making an extended graph or a complete graph. Here I put the two kinds of arrow with different case, different weight. And you can see that we have those related in the complete graph. This is the same kind of graph that we see in the first slide. but now we can show how we can put apart these two characteristics of this kind of structure that we have. Okay.
Yes.
And then now we are going to speak about some properties in general of operations that we can build in graph. The first of this is the path in a graph. Path in a graph can be think like a word built with the edges of one graph. Then the sequence of these edges are saying to us that we are traveling in the graph. One special kind of path are cycles. Cycles are closed paths, but are closed simple paths. That is, the each vertex only appears one time, and then we can different kind of cycles in the graphics that we are discussing now. Okay, we can see different cycles for for a complete graph. I put different the different cycles, only separating those for the arrows with weight 1. The black arrow are the arrows with weight 1, and the red one are of weight -1. Then we have here this, and you can see that either we can get one cycle, one closed cycle in different ways, either starting from the same point. Then we can get one special vertex for define this starting point, and then we can build different kinds of cycles. In our past meeting, Professor Page, I made a mistake because I presented this like trees, but not. This was not correct, because the combination of arrows of different weight cannot be trees. In fact, a tree needs have not cycles, and then we cannot combine in a tree these two kinds of arrows. Then the correct graph that I showed the past meeting must be cycles that are showing in this opportunity. But this can this can be presented starting from here in this way. Then for this, we need another kind of graphics that are opposite graphics. Then I put it here the definition of a direct graph again that are a set of objects called the vertex and a set of arrows called edges, and two functions that are the definition of the direct graph. These functions are the domain and codomain of the edge that here is noted like T, the domain, and S, the codomain. Then from this direct graph, we can build an opposite graph, and the opposite graph is wielded only inverting the functions that we use for this definition. Because
I have a formal question.
sorry, excuse me. I
have just one formal question. With this definition, there's no restriction that prevents us from writing that S is equal to T, right? But in the previous diagrams that you drew, you did not show any situation where an edge connects a node to itself, right? So you said that edges had weight 1 and weight -1, but if there are edges that connect a vertex to itself, is that a weight 1 or I don't know? How do we assign a weight to an edge which is?
Sorry, go ahead, please.
So what I mean is, I don't know if I can do this here. Yes, okay. I think I can draw here just temporarily.
Okay.
What I'm talking about is we might have some vertex, and then we would have an edge that looks like this. Oop. What happened here? Okay, I meant here. Right? Oh, it disappears. Sorry, I must be using the wrong option. Okay, come on.
And you can, you are trying to draw in the.
Yeah. Why it disappears?
No, you don't see anything.
Oh, that's annoying. Well, what you cannot see me drawing anything?
No, we only see Jesus' screen.
Yes,
Yeah,
I don't.
but I'm trying to draw on his screen.
Oh, no, we don't see anything.
I'm going to see about the possibility of sharing, because I am sharing here from my computer, not from my not from my iPad. Then maybe I need to give rights to you.
I'm not sure. And this is something I normally do when I have meetings with other people. Is I, they make a presentation, but sometimes I can point to something or
Well, I see an arrow. Is that your arrow or is that Jesus's
yes,
arrow?
no, it's my arrow.
Okay, I see your arrow. But it's not marking anything.
That's very strange.
Because here I can see the option for disable annotation for others, but this means that it can be made.
Well, it's not so important. I think I can describe. Yeah, you're going to maybe can you go just to the first graph, first slide that
Okay.
contained the diagram?
Okay, then here.
Yes, that's sufficient.
Okay.
So, so on the left-hand side, we have 3 vertices, right? And we have well 6 edges, I guess. But there are no edges that go from a given vertex directly back to the same vertex.
Loop. No loops.
A loop of length 0,
Yeah.
I suppose, or a length 1 maybe is better to say. So the only loops that we have in these graphs have at least length 2. Okay? So we go from one vertex to a second vertex and then back to the first vertex again. So we could call that, since we traversed 2 edges, we could call that length 2 cycle. But we could also have length 1 cycles that go from the vertex back to the same vertex with a single edge, like an identity, right? Like
Yeah, just a plain loop.
Yes.
Yeah.
Here are the definition of the weight of the arrows, and then
but imagine an arrow that goes from one vertex back to the same vertex.
Yes, but in the case of complete graph, we are only considering the relation from one vertex to all the other vertex.
Yeah, we don't have
No.
loops.
But not to
But
itself?
we don't have loops in a complete graph.
But then I had, that's why I waited to ask the question, because when you gave the definition, the formal definition of the graph below, you did that in
Okay.
such a
The
way.
formal definition is here.
Yes, here.
Oh,
yeah, no, not
oh,
that.
no,
This one, no.
Here,
This one, yes. So
Yeah.
so this is where I asked the question. And so my question was that you have these 2 functions, what you call it? Dome and codome, right? Or you could call them source and target.
Yes.
But you have
Mhm.
no restriction to say that S cannot equal T. Right? So if S is equal to T, then that means we can have an edge, which is a loop, right, on itself.
Yes, but this is in general for a direct graph. This is the definition for a direct graph. But in particular, a complete graph have not this inside the definition. There are not considered in general loops in complete graph. But here the important one is the opposite graph, because from any graph we can build an opposite graph only inverting S and T. This is the important questions, and I am go back to complete graph now, but for identify in the graph a direct graph and one opposite graph. This is the idea for this slide. I understand the point that you are expressing now, but in the case of a complete graph, we have not loops, not yet.
Okay,
Because
so show us a directed graph and its opposite. You haven't showed us that yet.
the idea is that a complete graph is built with one direct graph and the opposite.
Oh, so they're the same then. A directed graph is the same as its opposite?
Yes, in fact, is the next slide. You can see here.
Okay.
Here we have a couples of opposite graphs, and those are parts of a complete graph.
Okay.
Then
So they have different orientations. Is that what the difference is? Left and right, say, those red arrows are counterclockwise, whereas the black arrows are clockwise. Is that the difference?
no, it's only for a presentation, only for presentation way, but then there are not a difference. Okay, we can say, if you like, that is the bend of the arrow is related with the weight of the arrow. But this was not the purpose for this presentation, but only for clarify the difference between them.
Okay, I have just one question. Why are you drawing figures like this, completely different? You could take those vertexes and put them anywhere on the graph, so it would look like the first slide you showed, more symmetrical rather than everything inside like that.
Yes, because in the first slide that I was showing is symmetric, is a nice graph, but is hidden these properties in the graph. Then
They're equivalent. They're still equivalent graphs, are they not? They're equivalent.
Yes, they are equivalent, and here until here, these are only presented in this way with the purpose of clarify this kind of properties. Until here, because in fact we can see one thing in this direct graph. In this direct graph, we can go. I cannot write here here in my own slide because the software that I am using is different, but we can think that the
These points
vertex
are the
that
same.
the point
Coincide.
vertex that are in the upper level are B1, B2, and B3. And it is important to see from here that we can go from B1 to B3 going in two steps, and there are some kind of equivalence in this in two different paths that we are making, starting from the vertex 1 to the vertex 3. There are two different kinds of paths that are equivalent. And this kind of equivalence is important because we are going to see that they are related with the these are related with the degree of the arrow.
Okay.
Then this is the principal idea for showing in this way. Okay, and then we can go to the next, and we are now to speak about tree graphs. This is a formal definition taken from one standard text for a tree. T is connected, T is acyclic, and T has n-1 edges.
But Clifford algebra is not used anywhere in your definitions. No Clifford.
No, not yet. Not yet, because we are speaking here not of categories, but we are speaking here about the graph. After we are going to, is my idea to arrive to category theory, and then we can examine different kind of algebras using these properties of graph.
Okay.
This is the idea. Then
So you're actually giving me ideas, and what I want to say, I can say something about what you're saying here, I think too. But when you finish, I would like to, I'll talk about some of your ideas here.
Okay. Okay, I'm going to show here the tree graph from the complete graph now. You can see that for this, we are modifying the opposite graph. And the opposite graph are modified by cloning the vertex 3 in the first in the first tree that I am presenting here. This operation of cloning we can see, we are going to see before, is important in this building process. But it is for now, it is important that these two arrows that I think that Professor Paces are correct in the name that he associated to them are 1, 3, and a co-tree. And these tree and co-tree are showing to us this kind of operation that we are using in this building process, because you can see that the first tree that we have here is only cloned again for get the next complete graph. But here we have only 3 vertex, and now we have here 4 vertex. And this process of cloning, sorry, not cloning, of grafting is the fundamental operation that we are using for building more complex complete graph. The next complete graph is only the process of grafting this inside the same graph.
So those arrows at the top don't go anywhere. They're not connected to a vertex, right? They're just, how many vertices are in this graph? Or on the right side?
In the right side, we have only 4 vertex that are the level of the tree.
Ah, okay.
Yeah. Mm-hmm.
Oh, okay. So you're not, okay, so, but there are 1, 2, 3, 4, 5, 6, 7, 8 vertices in all together, right?
Yes.
Different levels though.
The different levels.
Oh, okay.
Equivalence to vertex. Now.
Okay.
No, I think there are only 4 vertices.
Yes.
And on the left-hand side, there are only 3 vertices.
Only 3 vertices. Yes. Mm-hmm. Because here we have 3 levels. Mm-hmm. 1 level, 2 levels, and 3 levels. Mm-hmm. And here 1, 2, 3, and 4. It is interesting.
Those aren't vertices then, they're levels. That's different than a vertex, isn't it? A level is not the same as a vertex.
Here in the representation of 3, the level is corresponding to 1 vertex.
Okay.
The level is corresponding to 1 vertex. And you can see one thing that is important. We have here 1 vertex in this level. Here we have 2 times the same vertex in the I need to correct because the level 1 is here. Then in the second level, I have only 1 time the vertex 2, and in the third level, I have 2 times the vertex 3, and in the 4th level, we have 4 times the level 4. Then this is the way that is growing the tree related with this complete graph of higher order. This is the idea here. And after we have then this grafting process, we can start with one graph. Maybe I had to put before 1 vertex only, 1 point. Then after we have one edge, and after we have in this process of grafting, then we put this graph here, and then the first one is growing one time. And then after I grafting this here, and then this is growing to one level more. And this process is important for understanding how we can go from simple complete graph to complete graph with more vertex. Okay. And then we are going now to see the relation, to start seeing the relation with algebra. Then we speak here about binary relations and a direct graph. And we can see that one binary relation is isomorphic to a direct graph. Here is only the definition of binary relations, in where we are using the Cartesian product for this kind of relation. Then for graph, X is are the vertex, and then the willing of a direct graph is a product, a Cartesian product of vertex. Okay, and then we more about the binary relations and the direct graph, and then we can see that one equivalent relations on a set X that can be a set of objects or a set of vertex, then we are going to build a complete graph adding to the definition that I presented before, the reflexivity and transitivity that permit to us to define a category. And now here is when we add the properties of reflexivity. Then reflexivity are associated with identity, and transitivity are associated with composition. I am using one definition of MacLean, and the property of composition is associative. Then we can use this kind of process of building for get one relation between a graph and a category here.
How about symmetry? What can you say about the symmetry? That means just vertices and no edges. Symmetry.
Yes, the symmetry is that there are not arrows in the edges.
Okay, so that's just vertices then, just vertexes.
Just vertex, but you can see, you can think in this like if you have two arrows in the vertex, and this is symmetry. Mhm.
Oh, but the arrows don't connect
Oh.
vertices, just an arrow.
If you have two arrows, two opposite arrows between vertex, then you get a symmetry relation that can be drawn like an undirected edge.
Oh, okay.
Mhm. And this is the idea here.
It's like 1 + -1 = 0, right? It's the same idea.
Yes, it is like this. Then the weight of the edge is 0. Mhm.
Uh-huh.
Mhm. And now here is the idea of category. Mhm.
So which is more general, category theory or graph theory? Which is more general?
More general is graph theory.
Graph
Because,
theory.
yes, graph theory, because for a category, you need to add to one graph the operation of reflexivity, no? And the operation of composition. And then you get one category in this.
Okay, interesting.
Mhm, mhm. Then this is in general the ideas that Professor Pace and I were
Okay, I find it very interesting. Just in what I'm trying to do right now as well. Maybe we can put it all together. That's what I hope.
Okay. Okay, here there are some reference. I can send to you this presentation by
Okay.
email.
There was just one item one topic that we discussed towards the end of the meeting last time, which had to do with types of duality, I guess.
Okay.
Because one of the types of duality that you mentioned just now in your presentation was the notion of an opposite, right? So that you could, if somebody gives you a graph, then you can immediately define a new graph called the opposite graph. And so the opposite graph is
Yes.
obtained by exchanging the source and target of every edge. And so this type of duality seems to me to be sort of fundamentally different than, say, the duality between a vector space and the covector space, or linear, the algebra. I mean, linear algebra and its dual, right? So it isn't. So the kind of this was sometimes called categorical duality because the same. I mean, the opposite graph sort of becomes the notion of a dual category. So sometimes, or maybe you could call it the opposite category, in which you've exchanged the source and target of all the morphisms in the category. And this.
Yeah, so I would think about that as, for example, two null vectors either a vertex dotted a vertex is 1/2 or -1/2. That would be how I would like to try to understand it, for example, in those terms, but we'll see whether that's possible or not.
Well, I think in the types of graphs that underlie your work, Dr. Sobchak, what I'm talking about amounts to exchanging the signs, right? So,
Well, actually, just what I learned in the last couple of days, it has more structure that can be put into it in a very easy way, which I will explain on page 5. I think I can explain it pretty clearly. So maybe it is general enough to cover these ideas. I'm not sure really, but well, I'll try to say more about it when Jesus finishes.
okay.
Okay. Maybe one thing that Professor Pech are trying to emphasize is the concept of duality here, because we need to work more with this property, because here these two operations, these two kind of categories are inside a complete graph. And then in this complete graph, we have the duality expressed.
You're exchanging edges with vertices. That's the idea, is it not? You're exchanging what's a vertex.
No.
that's
Exchanging
not true.
source and target.
But that's not the same thing as saying exchanging edges and vertices.
Not
No,
at all, no.
not at all. And the vertex in the two graphs are the same.
Okay.
They are the same, the vertex. But you are only changing the direction of arrow that is changing domain by codomain.
Okay.
And this is too much important, because the change of domain and codomain.
Okay. Yeah.
Yeah.
Okay, okay, I get it.
Okay. Then, okay, I'm going to stop the sharing now.
Okay. I think that you'll be able to see a connection to what I'm going to present. Very interesting. I think maybe it can be developed together, I hope.
Yes.
So shall I try sharing my screen?
Yes, please go ahead.
Okay, let me see if I can do this. I've got to see my screen first. I haven't seen it yet. Okay, let's see. Okay, one more time here. Oops. Okay, let me pull it down. Okay, there it goes. So I want to go here. Okay, I'll make that small. And let's see here. I'll try sharing. Hopefully it'll pick it up. I don't want this, I don't think. Okay. And what I want is this. Can you see that? Maybe not.
Not yet, no.
Okay, let's see if I can do that. Okay. Okay, this is what I want right here.
Now we have.
Okay, let's
It
see.
looks good.
Okay, let me make it big here. Can you see that now?
Yes, that's fine.
Okay. Let's see if I can get this out of the way here. Okay, so you see my first screen, nilpotent geometric algebras.
Yes, we are receiving.
Okay, so what's important here are these two tables. So, okay, so remember, we're talking about nilpotent. So a nilpotent is just a quantity that has square zero, but is not equal to zero. Okay, that's a nilpotent. And we say nilpotents are linearly independent if when you take the outer, I don't even really need these two definitions here, but this definition of correlated is very important. Okay, so two nilpotents are said to be positively or negatively correlated if AI times AJ plus AJ times AI is equal to 2A dot I dot AJ is equal to 1 minus the delta function. So in other words, when I is not equal to J, it's just equal to plus or minus 1. But if I is equal to J, then of course it's just saying that it's a nilpotent then. Saying that AI squared, 2AI squared is equal to 0 then. Okay, so in the case where you have positively correlated equal to 1, okay, then you have this multiplication table. For any AI times AJ, you get this table here then. And it follows from this relationship right here, AI plus AJ, AJ plus AI equal to 1. If you multiply that by AJ on the right, then you get AI, AJ, AI plus, plus AI, AJ, AI is equal to the dot product, then, as we usually define in Clifford algebra. On the other hand, if they're negatively correlated, that's when you have this thing equal to minus 1 instead of plus 1, then you have this table of multiplication. So it's very close related, and it all follows from this basic definition here. One definition for how to multiply these nilpotents, or when they're positively correlated. If they're not correlated at all, then they're just a Grossman algebra. And they commute with each other then, if they're not correlated at all, as in Grossman algebra then. Okay, so, well, that's just a definition. I use capital AK to represent the sum of K nilpotents, A1 to plus A2 plus up to AK. And I claim that with this multiplication table, it generates the geometric algebra G1n, consisting of one vector which has square plus 1, F1 up to Fn, which all have square minus 1. And I don't allow, we can have any field over any field except characteristic not equal to 2. So that's important too, but I only want to consider the real numbers here. Okay, so these are negatively correlated. So I'd like to tie that into the graph theory that Professor Cruz was talking about. That actually just changes the direction of the arrow, I would think. Okay, so, okay, I'm not really interested in going through these ideas, but I'm just saying how you can relate this geometric algebra, E1, F1 up to Fn with this positively correlated. So I'm taking this multiplication table as being more fundamental than matrix multiplication. So this is the only multiplication that I'm assuming between these nilpotents. But that's actually another way of defining this geometric algebra G1n, okay, which I consider extending the real number systems by this orthonormal system of vectors. Okay. Now, if they're negatively correlated, then that's actually generating this geometric algebra. You have n vectors which have square plus 1, E1 squared equal to up to En squared equal to plus 1, and one vector with minus 1. We're considering these nilpotents that are generated by that geometric algebra satisfy this multiplication table. So these two multiplication tables are completely general for any AI and AJ, two nilpotents, and I can have any number of those things. Okay. Okay, so I define the algebra generated by these correlated, positively correlated null vectors. I define that to be 1 comma n plus. Okay, that means that the inner product of any two nilpotents is equal to, well, here it is, the relationship again that we had, plus that. Well, I give an example then. So if we have x equal to a1 plus a2 just for real numbers, x1 and x2 and so on, then we have these basic identities, just an example here. And okay, now what I'm doing is I'm saying, I'm giving you an example with 8 nilpotents, A1, A2 up to A8, and I'm using the matrix of transition between the bases E1, F1 up to F7. It's just a transition matrix relating the bases of nilpotents, correlated, positively correlated nilpotents with this matrix here that gives you the relationship. So what the idea is, you can always extend this just by extending the table. The formula that relates that is a very simple formula given by this formula. Fk is equal to alpha k times capital AK, that's just A1 plus A2 up to plus AK, minus K minus 1 times AK plus 1. Okay, so that's how we're generating this table here. So that relates the basis of nilpotents for this geometric algebra to the standard basis that people use, orthonormal basis with E1 squared equal to plus 1, F1 squared equal to F2 squared up to F7 squared equal to minus 1. So that's the relationship between two bases. Okay, so then the inverse relationship, just multiply the matrix T8 inverse times both sides of the equation, and you can relate the standard basis of the geometric algebra to the basis of nilpotents then. Okay, so there's the inverse. So given this matrix, just find the inverse of that matrix, and you find it's equal to that matrix. So that's just a interesting calculation. And again, okay, so let's just again, we're taking the table 1. I'm only going to look at, that should be A4, okay, not A3, because I have A1, A2, A3, A4. So, well, yeah, that should be A4. I made a mistake. That should be A4 here because we have A1, A2, A3, A4. Okay, well, let's just look at the example of A1 wedge A2 times A3 wedge A4. Well, if you calculate it out, that's the dot product of two bivectors plus the wedge product. So you have, and it's equal to, if you calculate it out, you can simplify it and see that this is equal to 1/2 A1 minus A2 times A3 minus A4 plus the wedge product, A1 wedge A2, the 4 vector then. Okay. Okay, so these are all distinct nilpotents. A1, A2, A3, A4 are all distinct. And this is a case where A1 wedge A2 times A2 wedge A3, so they have a common vector, nilpotent in common. And if you calculate that out using table 1, again, we're only looking at positively correlated nilpotents, you get this relationship. Okay, and if you look at the table, if you look at the first three, A1, F1, and F2, you find that E1 is equal to A1 plus A2, F1 is equal to A1 minus A2, F2 is equal to minus A1 minus A2 plus A3, F3 is equal to this, and so on down the line. That just follows from these tables here. So that's E1 plus E2, E1 minus E2. No, I'm sorry. That's the other way around here. Okay, so this is, so that's relating E1, F1 up to F7 to the nilpotent basis, A1 up to A8. Okay, that's this relationship here. Okay, so if we take T8 and multiply it by E1, F1 up to F7, you find that A1 is equal to 1/2 E1 plus F1, and so on down the line then, using these tables here then. Okay, and I'm just giving an example now. What you get when you multiply A1 wedge A2 times A3 wedge A4, you get this relationship. So you can see how that's. Okay.
Excuse me, Professor Garrett. Can you remember to me how do you get the TH?
Okay, yeah, that's given this first relationship
Yes,
up here. That's where it's defined right here. Well, that's for N1. So that's what table 2. But table 1 is what we're really, so that's this multiplication table. And here we have multiplication table 1. And okay, so I'm defining that here. Okay, right here. So GN, well, oh, right here it is. Okay, G1N. So that's equivalent to the algebra of nilpotents. 1 plus, they're positively correlated, and there are n plus 1 of them, A1 up to AN plus 1. The relationship is AI dot AJ is equal to 1 minus the delta function. That's just saying that they're nilpotents. When I is not equal to J, then that's 0. And so they're, that's AI dot AJ is just 0 then. But no, if I is equal to J, then that's equal to 1. So that just says AI dot AI is equal to 0, or that's the same thing as saying AI squared is equal to 0. But if I is not equal to J, then that's 0 here, and we get AI dot AJ is equal to 1/2. So all the inner products of AI dot AJ for distinct I and J are equal to 1/2. That defines the geometric algebra G1N. And the relationship is, okay, where did I give the relationship? Well, okay, I'll go back up again. Okay, right here. GN1N is the same as A1 up to AN plus 1, where E1 is equal to A1 plus A2, F1 is equal to A1 minus A2. Well, that's the same as this, but Fk is given by this formula, alpha K times AK capital, that's just A1 plus A2 plus up to A plus AK minus K minus 1 times AK plus 1, where AK is defined by this relationship. So that gives you then the geometric algebra, no, that's this geometric, G1N, using this basic multiplication table. That completely defines the geometric algebra G1N. So I'm really not using matrix multiplication anymore. I'm just using this table, which will become clear in my last page. So I don't want to spend all my time on that. But then I'm just giving examples for multiplying. So for x equal to x1 a1 plus x8 equal to x2 a2, a linear combination of these nilpotents, a1 and a2, positively correlated because we're in that algebra. Then I'm just giving examples. X2 squared is just equal to x1 times x2. X dot v1 is equal to this. Well, they're simple identities just using Clifford algebra then for that geometric algebra. Okay. Okay, and okay, if I take two of them, then if you take x1 wedge, x2, x wedge y, that's just the determinant, y dot x, y squared, and x dot y. Okay, now here's I give the formulas for n plus 1 equal to 8. So n is equal to 7. And the relationship between the nilpotent bases and the standard bases, E1, F1 up to F7, is given by this matrix T8. Okay, so notice that we can extend to the next A9 by the formula I gave, but I'm only taking it up to 8 because you can see it just generalizes this table that we're looking at. So that tells us that the nilpotent basis is related to the standard basis by T8, this matrix right here. That's for positively correlated nilpotents, all have the inner product equal to 1/2, A1 to A8. Okay, so okay, let's go on then. And that gives you the inverse, just the standard inverse of the matrix. No, and I'm just giving examples here. If we multiply A1 wedge A2 times this, we get that. I'm not going to go through the details because I want to spend most of my time on the last page, but you can look at these and it's just standard Clifford algebra identities for the wedge and the dot product then. Oh, but this is, okay. Okay, okay, so this is my important page that I wanted to talk about in more detail here. Okay, so now I'm just trying to redefine these things in a simple way. So I'm defining this algebra of nilpotents over any field as the A1 up to AN over the field. It can be any field, but not characteristic to, so it includes the finite fields. And again, I give the same relationships that I gave on the first page there. AI times AJ equal to AJ times AI is equal to 2 AI dot AJ plus or minus. Well, if they're positively correlated, I'm only using the plus. Negatively correlated, 1/2, the minuses. Okay, and that's what I'm saying here. If all null vectors are positively or negatively correlated, we write AN plus or AN minus respectively. Now, this is okay, so I'm going to, okay, so I'm just saying again, the multiplication table 1 or table 2 are fundamental to these ideas. And they basically define the algebra of nilpotents, AN plus or AN minus. Okay, and now I'm giving the examples here. I'm only going to talk about over the real numbers. We choose F equal to the real numbers. So all I'm talking about now are the real numbers over the real numbers. So given any two distinct AIAJ, then if you take the square of that, AI plus AJ, well, you get, what do you get? You get AI squared plus AI times AJ plus AJ times AI. Well, they're nilpotents, so this is 0 and this is 0. So what we have is 2AI dot AJ. That's saying that AI dot AJ equals 1/2. Okay. Similarly, let's take, this is very important. If you just change, this is something I didn't realize to how general it is until just the last couple of days when I was thinking about telling you about this. So look at AI minus AJ. What do we get? Well, just do the same calculation we did here. We get AI squared, AI times AJ minus AJ times AI. We get this. Oh, but this should be a plus sign. That's a mistake. Of course, it's plus because it's AJ AI, AJ minus. So it's just, that should be a plus sign. Okay. So we get minus AI AJ plus AJ AI, but that's equal to 1 because we're positively correlated. But AI squared, AJ squared is equal to 0. So again, we get AI minus AJ, should be a plus. That's awful. It's equal to -1. Okay. Then I claim from these relationships 2 and 3, which is really the same thing as 1 and 2, which are presented on the first slide. Now I'm showing really how we can define, just start with this algebra, forget about matrices altogether now. Define Fk equal to A2k minus A2k minus 1. So in other words, Fi times Aj, okay, this is the important thing. There should be a plus sign here. It's Ai Aj plus, okay? So Ai dot Aj is equal to minus 1/2. Okay, the idea here is if this property here is equal to Ai wedge Aj implies that Ai minus A1 minus A2 times A3 is equal to 0. Why? Because A3 dot A1 is equal to plus 1/2. A3 dot minus A2 is equal to minus 1/2. So that's saying that this vector A1 minus A2 is orthogonal to any k vector, A3 wedge A4 up to AK. Well, it's actually a k minus 2 vector because I don't have, okay? So all I'm saying here then, if you multiply A1 minus A2 times A3 wedge A4 up to AK, that's the dot product of this thing will be 0 because A1 dot that is 0, which is what we're saying here. And A1 wedge that, and then A2 dot minus A2 dot is also 0 because minus A2 dot A3 is minus 1/2 and minus and minus 2 dot A4 becomes plus 1/2 because remember we're taking the dot product of that bivector. So what I'm saying is that has to equal to A1 minus A2 wedge that. Okay, so that gives us another way. Let's just look at, I call it brute force, that any geometric algebra GPQ can be represented as a subalgebra of G of A plus of positively correlated n null vectors, where n now is just equal to 2 times A 3 times P plus Q. The proof is by constructing a standard basis vector of GPQ out of the anti-commuting vectors and trivectors of the larger geometric algebra. G0 2 times 3P plus Q. The idea is amply illustrated for the geometric algebra G1 3, that's the Dirac algebra, as a subalgebra of G0 12. Now, what am I doing here? I'm saying let's define gamma 0, which is the usual Dirac matrices, if you want to think about it as a matrix, as F1, F2, F3 of the standard anti-commuting vectors, F1 squared equal to minus 1, F2 squared equal to minus 1, F3 squared equal to minus 1, and they're anti-commuting. Okay, gamma 1 is equal to F gamma 4, gamma 2 is equal to F5, and gamma 3 is equal to F6, because notice F1, F2, F3, F4, F5, F6, they're all anti-commuting vectors, okay, because F4 anti-commutes with F1, 2, and 3, so it's that says that F4 is anti-commuting with gamma 0. F5 is also anti-commuting with F1, 2, 3, and F6 is also so these vectors F1, F2, F3, F4, F5, X6 are all anti-commuting. So in particular, we choose now as vectors. That's the thing, we're redefining vectors in the larger geometric algebra in terms of, well, now you can see, what have I done here? Well, actually, the seed I sent you, I said G06 because I'm just using the standard basis, but I can use also where F1 is equal to A1 plus A2, F2 is equal to A3 plus A4. So I can also define it in terms of 6 null vectors, positively correlated null vectors. So you can see I have to, probably to make it more understandable for you, I must write this out in more detail. But that's basically the idea. So the idea is we can, we're redefining what's a trivector as just the standard time-like vector gamma 0. The real direct vector gamma 1, we're identifying with gamma 4. Gamma 2, the direct vector or matrix, which has square minus the identity element in matrices, is now identified with F5. So that would be Professor Cruz's more general pictures of these graphs changing the direction of the arrows. Well, you can think about it as internal structure. So in the larger geometric algebra, we're thinking about a vector in G, the Dirac algebra, gamma 0, having internal structures defined by these by this trivector, F1, F2, F3, where they represent vectors in the higher dimensional geometric algebra. So but these things all anti-commute because a trivector commutes with this vector. So you can see we're much more general ideas that we're talking about, and I believe they correspond to the more general graphs that Professor Cruz is talking about. So that's the main idea, but I would have to make it more understandable. But I hope that what I presented here will help you understand, because I don't think it'd be that difficult. This new basis where I'm defining, okay, let's go back here where I'm that there are more definitions that are possible. The idea is that we're taking this table, well, let's go to this. Let's only consider table 1. So we can take any number of nilpotents, A1 up to AN, and just define the multiplication of those nilpotents by this multiplication table, table 1, and that's it. Satisfying, okay, where is this relationship? We know that the algebra exists, G1N, by making this identification, as I wrote here, that completely is just a change of basis of that geometric algebra. But now, okay. Well, okay. But notice here, I'm defining these standard, these are vectors, fk squared is equal to -1. But now I'm defining it in terms of a2k minus a2k minus 1. Well, in the simplest case, that's the same thing as defining, well, that's the thing. It's always a little more confusing when we write this as 2i times 2i minus 1. It's not really confusing, but you have to think about it a little more than if you just take an example. So fi times fj, think about I equal to 1 and j equal to 2, okay? So we have f2 minus f3 times, okay, then 3 and 4, f3 and f4 give you, in terms of all these nilpotents. Well, anyway, I'd have to go do more detail, but I hope that, but the basic idea is for the Dirac algebra, the simplest way, but there's other ways of doing it. For example, we can use these relationships where f1 is equal to, for example, this third one, f1 is equal to T inverse is this relationship. That's minus A1 minus A2 plus A3. So that would be your graph with 3 vertices, or that's what I'm thinking about. The minus signs, you can see we have all kinds of possibilities to identify these vectors F1, F2 by various relationships given in this table for the first 8. But the table can be extended to any number of dimensions. Keep going down the line. There's many more possibilities for extending F1, F2, F3, and so on. But I just have to write more and to make it more understandable. But I'm hoping that what I sent you will be enough for you to start understanding what I'm talking about.
Okay, well, I do have one, I think, simple question. Are you still there? Hello?
I can stop sharing if you like, or go to another slide.
No, just a minute. I seem to have, so I had a temporary internet problem there. I guess I was, can you hear me now?
Yes.
Yes, we can.
Okay, yes. So I had a simple question. I think if we go to page 5, here, yes, so here on page 5, we're almost there. Yes, you're considering a fairly complicated case, but
The simplest case is 8, 2, and 3. That's the most fundamental, 2 and 3 here.
well,
It's pretty simple, really, but there's a mistake. That should be a plus sign, not a minus.
I'm sorry, I'm not quite seeing what I was hoping to see. Let me check my own copy here of what I looked at earlier.
Yeah, this is a little different. What I sent, the last page is slightly different, but that should be a plus sign here. I don't know why I did that.
Okay, could you go down to the paragraph that starts show by brute force?
Oh, okay.
So, yeah, there it is. Okay, so the main claim here that I see is that G, P, comma Q can be represented as a subalgebra, right?
Exactly, but we're reinterpreting what are vectors.
Yeah, understood.
But just so long as that they're anti-commutative and square -1 for the F's. That's all that's required. And that's what we're defining in terms of the null vectors.
Yes, all that's very clear. But you're illustrating with a rather complicated algebra, the Dirac algebra.
Well, that's right. I'm not really interested in there's many different ways of representing it as a subalgebra by reinterpreting what are vectors in that algebra. And
Sure.
I'm just saying that it might be
that's
for more
clear.
general graphs, you might want to take these higher dimensional cases or more of these vectors, the nilpotents, because everything can be named by nilpotents, which we want to name vertices of graphs by nilpotents.
Yes, that's all very clear. No problem at all. But I wanted to consider a much simpler case.
Okay.
For example, G1, 0. Right?
Okay.
So what sort of representation do we get from G1, for G1, 0?
Okay,
now,
so
1,
I would
0.
Yeah, so I could represent that as A1 plus A2, where those two vectors have square 0. They're nilpotents. And of course, the inner product is 1/2. So that represents E1 then is equal to A1 plus A2. So I represent the geometric algebra G1, 0 as A plus 2. Okay. It has two nilpotents, A1 plus A, A1 and A2. And E1 is just equal to A1 plus A2.
Now, G1 comma 0 is a relatively simple algebraic object, right?
Yeah. And G1, 0, 1, I could represent, well, that's the thing. That's the exceptional case, really. G01 is equal to A1 minus A2, because if you square A1 minus A2, you get -1. Okay. But again, that's a little bit confusing because the mention of the geometric algebra G01 is one-dimensional, generated by the vector E1, but it can also be generated by one vector, which I call A1. I'm decomposing E1 into the sum of two nilpotents, A1 and A2. So that corresponds to two vertices. And the square, those are the symmetric case that Hayes would call the symmetric case.
But I wanted to understand what this representation means in this one of the simplest possible cases, right? So,
Okay.
So G1 comma 0 is just the real numbers, right? Or scalars.
Well, just a unit vector, which has square plus 1, okay? Because A1 plus A2 squared, if they're positively correlated by 1/2, the inner product is 1/2, then you get A1 plus A2 squared is equal to 1. Well, that's just like the unit vector E1. But you can see I'm representing E1 as a sum of two null vectors, A1 and A2, which I would think as vertices of a graph with no arrows between them. That would be my symmetric graph of two vertices defined by the null vectors A1 and A2. And the other algebra, G01, I would define as A1 minus A2, because A1 minus A2 squared is equal to -1. So that corresponds to F1. That's what I call F1.
So G01 is that isomorphic to complex numbers?
Yes, exactly. That's one isomorphism, but it's also isomorphic to the algebra consisting of two null vectors, A1 and A2, by just one vector by A1 minus A2, because A1 minus A2 squared is equal to -1. So it's a subalgebra. You can say G01 is a subalgebra of A2 plus, okay? Well, that's A1 minus A2. It's a subalgebra generated by A1 minus A2. I guess it's a subalgebra, right? Because if we just have one element, you can't get anything else. Well, let's see. Yeah, I think that's okay.
I'm just finding it sort of interesting to at this level anyway to understand the structure of this A plus algebra.
Yeah, that's why the most basic relationship is given in these two tables for the first 8-dimensional. You see this, the one we're looking at is just A1 and A2. That corresponds to this. But notice that that's a little bit exceptional case because we're on the first and second lines of this matrix here. It's not diagonal. All the rest of the elements are diagonal. So if we cut out that block, 1/2, 1/2, 1/2, -1/2, the rest of the matrix is diagonal. Well, except for these ones down the line. So that's so in a certain sense, that's the exceptional cases. The first two lines, that's where E1 is equal to 1/2 plus A1 plus A2. All right, and well, let's see. That's the inverse here. Oh, where is it now? Yeah, so that's A1, A2, A3. E1, put the A's down here is 1/2. No, what am I doing here? I get them confused myself. Yeah, A1. Yeah, E1 is equal to A1 plus A2. So that is using this graph right here. So we put A1, A2, A3 down the line here. And E1, where is it? Well, I guess it's right here. Yeah, E1 is equal to this graph. That's 1, 1 times A1, A2. So it's A1 plus A2, whereas F1 is equal to the second line of the inverse. That's what's confusing here, my graphs here, is A1 minus A2. A1, A2, it's A1 minus A2. But after that, you can see it, the dimensions correspond. 1, 2, 3, 4. We have the geometric algebra E1, F1, F2, F3, okay? But again, that's a mistake. That should be 4 there, not A3. It should be A4. I have to, yeah, that's a little confusing because it should be A4 because it has 4 nilpotents. But that's because of earlier notation I was using. I haven't corrected it all. But I'll write more up, try to make it more understandable in some simple examples. But I was trying to, like with this definition, I'm trying to define F1 as in terms of this relationship, A1 minus A2, okay? And then F2 is A3 minus A4, F3 is A4 minus A5, using the basic multiplication tables of these nilpotents given in table 1. In this case, I'm only considering table 1 here, this table. That's the interesting thing. I think this multiplication table 1, well, that's the negative case, but characterizes the geometric algebras G1n in a unique way without matrix multiplication. But I can, you know, it's compatible with matrix multiplication. So, but I need to write more up to make it more clear, and I can do that. I like to combine it with Professor Cruz's examples. It looks to me like by reinterpreting what's a trivector in terms of reinterpreting what are bivectors and trivectors and vectors by anti-commutative property, that we can get the same structure, but now that corresponds to the internal structure of a particle, or if you like, by a graph. Or apparently it's, from what Professor Cruz says, that's also more general than category theory, which is interesting to me because I don't really understand the language of category theory, but I do understand the language of Clifford algebra, which in this more general sense maybe encompasses category theory now. It seems to be a possibility. So, but I need to write more simple. The next thing I'll talk about is just simple examples and not the more general cases, which just makes it harder to get to the notation.
Yeah, I think that would help me, for example, just to get started, is to look at simpler examples.
Yeah, that's right. It's too general right now, but basically the basic idea is table 1 and table 2 with this relationship 1. That's all. But I want plus sign. I only want to look at plus, not minus anymore. The other is very interesting too, because like I say, I've just in the last couple of days, I've gotten new ways of looking, well, which correspond to the higher dimensional graph theory, I believe, as well. But I'm sorry that's another problem I have drawing graphs. I can't draw nice graphs as Jesus can do. And that's a limitation I have. I just don't have the software or mastery of. I know that some of these programs, like what is it, Gallup or whatever exists, but I've never learned to use these programs. So I'm stuck trying to use Mathematica, but I have an old version of Mathematica, which does not have that capability. So anyway, I'm limited what I can draw on my graphs. So that makes it more difficult.
I still have, at this point, I'm still don't see any strong connection with graph theory at all, really.
Okay. Well, I'll try to make that clear next time. But I think it also, you agree then that quantum mechanics has a lot to do with graph theory, which is more general than category theory. I guess Professor Cruz will agree with that because, well, that's what Zbyszek has been trying, Dr. Ojevich was trying to do, is related to category theory, which is, if I understand what Jesus said, is more general than category theory.
Well, graph theory just has fewer axioms, so it's only general in that sense, right? So a category is necessarily a graph without composition.
The category theory is one restriction added to graph theory, because we need reflection and we need a composition. And then in this way is more general, because there are not a structure. The degree of structure is lower in graph theory.
So
Okay.
I would interpret Dr. Oshevich's interest in category theory from a somewhat different way. Is that category theory, in a sense, is more general than algebra, I guess, right? Because so the algebra has a fairly complicated structure, but a category that underlines an algebra is more abstract. Like it encompasses a whole family of algebras and the relationships between those algebras. So it's not so much that one would need to go to graph theory to be even more general, because it isn't any clear sense in which the graph theory underlies algebra. Right?
But I think there is. I believe there is. Okay.
Graph theory,
what I would suggest,
but let me just make one more point, and that is that graph theory doesn't have any concept of composition. So we can't take two edges and make a third edge. There's nothing that we do within the category or within the graph that does that. Right?
No, but we can do that algebraically if we say that two graphs are connected by an edge, two vertices are connected by an edge if their inner product is equal to 1/2, for example. You can assign an algebraic operation to, well, for example, that's what people do when they assign what is it called, a matrix to a graph. So you can algebraize graph theory by various algebras. One way is by using matrices, but I suggest that it's better to use different algebra.
You can add this kind of operations if you define composition. And if you define composition identity, you are in category theory. But not before. In general, in graph theory, you can get one representation of one algebra, but only with identity and with composition.
Okay, so you cannot say that category theory is an algebra. It's not an algebra.
It's not an algebra.
Okay, but I think it should be possible to make it into an algebra. That's exactly what we do. We call it geometric algebra because we're creating an algebra to represent geometric relationships. So geometric algebra. So why can't there be a geometric category? Well, in fact, if you can represent a category by a graph, and if you can algebraize graph theory, then it follows that you can algebraize. In fact, that's what people do with adjacent matrices. That is a way of algebraizing at least the relationship of edges to vertices. And you create a matrix to represent that relationship. And then you can do algebraic operations on matrices, which represent properties of the graph. So that's an algebraization of part algebraization of
But
graph.
one graphic is only one relation between vertex and edges.
Okay, but I'm suggesting that there's more deeper ways of representing algebraic properties, right, of category theory, of graph theory.
But you have not defined there any kind of operation that can go to take to you to say what how you can compose two arrows, for example.
Okay, I agree. But let's say that I agree with you. But let's say that for the next time we study a graph with 4 vertices, all possible graphs with just 4 vertices, and I will write about an algebra with 4 nilpotents, A1, A2, A3, A4, which are positively correlated in various different ways. And let's see if we can algebraize what you present with 4 vertices, what I do with 4 nilpotents, which are positively correlated, or maybe negatively correlated, either one. How does that sound? Limit ourselves so we can write very simple, the simplest possible pictures to communicate better by very simple, the simplest possible example. I want to take 4 vertices, not 3, because that's where you need, well, you need more than just complex 2x2 matrices, I believe, to represent them. You need maybe 4x4 matrices or whatever. But if you want to take 5, but maybe just 4 or 5, if you want to do 5, if it's more interesting, that's fine too with me. But, or just 4 and 5, if you like, maybe that's good.
But I think
But just lower number, not more than that.
You need to define more clearly what you mean by all graphs with 4 vertices. I mean, there's an infinite number of graphs.
Okay, but I think
even with
how you can do that.
Even with 1 vertice, there's an infinite number of graphs. Right?
Well, that's right. If you have loops, what infinite number of loops connected to it. But that's fine. That's fine. I'll try to show you how you can do that with nilpotents.
So say we had started with just 1 vertex.
Okay. So that's A1 squared is equal to 0. And now we can, well, anyway, let me think about it a little bit. And like I say, that first 2 cases are exceptional in the sense that after that, that matrix I represented here, you can see this first square here is different than the rest of it. And that's significant, I think, as far as what we're talking about.
So this T8 matrix is diagonal except for the first row.
Yeah, that's right. The first row represents A1 is equal to E1 plus wait a minute, see, I get it. Yeah, E1 is equal to A1 plus A2. Okay, so that's the inverse one. So A1 is equal to 1/2 E1 plus F1. Okay, that's A1. And F2 is equal to, that's F1. No, that's E1. Okay, then F1 is equal to 1/2 A1 minus 1/2 A2. No, I got it. I'll write it out next time in a clear way. It's so easy to get confuse these things. But anyway, but like I say, if we can limit to 4 or 5 vertices and try to, and I'll try to do the same thing, and maybe we can do something more to try to put these ideas together. I need to do more work, maybe. Well, it'd be interesting to see what Professor Cruz has to say about it, and whatever. I don't know. I will make the corrections. It's terrible. I made such little mistakes, which add to the confusion, of course.
That's
Okay, I'll stop sharing.
That's just fine. Don't worry about that.
Okay, so I'll stop sharing and then.
Okay.
All right.
Okay.
Here we are. Yeah, I think it's probably would be appropriate if we wait now our usual 3 weeks, what's become common for 3 weeks.
Okay.
I'm not sure at that point, Eustace, did you want to add more comments about graph theory, or should we maybe continue with Clifford algebra?
Yes, now until that I have presented today. I started with category theory. Then my idea is to continue, but now in the in category theory, trying to use the properties that we saw in graph, and now to formalize inside the category theory, and then try to relate it with algebra.
Okay, that's exactly what I want to do.
All right. Well, then perhaps in 3 weeks' time, we could use a similar format as today. We could sort of begin with some presentation about category theory and its connection to graph theory, and then maybe from your point of view, I guess you're sort of proposing that category theory provides this bridge, right, between sort of, or at least it's something intermediate between graph theory and algebra. Was I guess Dr. Sopcich is suggesting, I'm not sure, maybe to see.
Well, what I'm going to do
graph
is
theory as sort of as related to algebra somehow.
Well, I hope that we can,
by algebra. So
I would like to algebraize category theory is basically what I'd like to do, but I'm only going to look at the simplest case of graphs with 4 vertices or 5 vertices, which are named by nilpotents. So that means I'm only going to consider nilpotents A1, A2, A3, A4, A5 at the most, just so I don't have to write, these more complicated looking expressions, even though it's more general, but it's just easier to see it. Now, of course, even with graphs, it might be easier to limit the number of vertices, then you don't get such complicated pictures too. And or even ideas with category theory too.
Well, from the point of view of category theory, though, graph theory is extremely simple. It just involves two morphisms. You know, one that says what is the source and what is the target.
Okay, but
You know,
is it
but
easy
there's
to do?
nothing more
Is it
to
easy
graph
to do
than that.
calculations with it? Ultimately, in graph theory, you want to calculate shortest path and all the other things that calculate. So, can you use category theory to efficiently calculate these other ideas that you need to be able to calculate to apply it? Graph theory.
But I would say no. That's not absolutely not the orientation to category theory at all. Right? It's
Why
something
isn't
like,
it though?
well,
You
it's
should.
because category theory plays a similar role to set theory in mathematics, right? So we don't try to use real numbers to represent sets, right? But real numbers are sets.
Oh, okay, so I think the ideas are important, but ultimately, in applications, you want to do calculations either with edges or whatever, which people use matrices for. The piecewise, they introduce algebra in order to do calculations which are interesting for them. But it'd be nice to have a more general algebraic way of approaching category theory, if that's possible. Maybe it's not possible, I don't know. But I think I'm beginning to think that it must be possible. So, but that's just my idea
Okay,
right
well,
now.
but just to illustrate the point, do you think it would make sense to say replace set theory with somehow with a subset of real numbers or a subset of some
No,
other
no,
algebra?
no. But if you want to do calculations with a given set, you want to, for example, you want to count the number of objects in the set, then you've got to make some association with the real numbers then, for example, or you know, Cantor sets and the rest of it. No, I understand what you're saying, Dr. Page, but well, let me just see what I can do with the, like I say, I'll concentrate my presentation on 4 or 5 vertices, which are named by nilpotents, and just see what I can do with it as far as relating it to category theory. Well, the graphs that
Well, okay, I think that's very interesting.
and in particular, I'm interested in the Dirac algebra, which is very important in quantum
but
mechanics.
again, I encourage you to keep it simpler
Yeah,
than that.
I agree.
Right, like even to go beyond. Unfortunately, I know you pointed out this sort of the simplest cases are somehow anomalous, right?
Yeah,
Something
the
like
first 2
like Lie
are anomalous.
algebra also has a simple, you know, like a similar sort of thing happens in Lie algebra, right? Where you have all these, you know, sort of non-standard sort of structures at the beginning, but then after you get large enough dimensions that you no longer get anything more anomalous. Everything behaves nicely after you're large enough. But still, the intuition goes away, right? When
Well,
you get
yeah, as far as Lie algebras is concerned, that was one of the main motivations of, you know, this book I have with Hestenes, you know, thinking about whether all Lie algebras are bivector algebras. Again, that's trying to algebraize Lie algebras in a meaningful way. But anyway, maybe I have some new insights into these ideas. In fact, that's what my presentation to this graph theory conference I told you about is related to those ideas, actually. Well, actually, with this conference with the Ojevich research conference that is related to Lie algebras there too. That'll be coming out sooner or later, I guess.
Okay, well, let's agree that we will meet then in 3 weeks, and I look forward to presentations like from both of you. Right?
Oh, so do I. That was very interesting today, what Jesus presented.
Okay, any other comments?
Okay. No more than in 3 weeks, you say
Okay,
we can meet.
Okay,
great.
Okay,
Thank
bye.
you very much.
take care.
Bye for
Bye.
now.